but it's still a lot of data. All right, thank you.
Great, thanks. Okay, so if you're a presenter and you haven't signed a consent form and you're getting up to present, go ahead and sign this real quick. It only takes like 15 seconds. So our next presenters are, well, I'm not, Luis. Luis is the presenter, yes.
Let me test this real quick just to see how. Okay, cool. I can't go. Can I go back?
Yes, look at the buttons there.
Yeah. It doesn't.
Not letting you?
Oh, there we go. Okay. So hi everyone, my name is Luis Rodriguez. I'm a member of the Johns Hopkins Applied Physics Laboratory, and today I wanted to talk to you about some of the technology that we've developed at the lab as part of the Dart flight software team regarding FPGA-Instantiated processor in the loop for flight software development. So it's a mouthful, but it's a very neat technology that I hope to share with you, and hopefully we can you can find some usage for it. So before I even get started, I wanted to thank the team. I'm representing an entire team of other flight software engineers who have made this work possible. So they're up there on the slide. So today, I wanted to talk about the DART mission. So this is the mission that pretty much started the technology that we'll be discussing today. And then some of the motivation, the reason why we developed what we developed, are current flight software development testing modalities, which in previous presentations you've heard about Swirl and things like that. So we'll go over those briefly. And then we'll also talk about what Dart has done up to this point regarding our flight software in the loop testing environment and our processor in the loop, or PIL, testing modality. And finally, we'll just go over a use case and discuss some of the future work that we're planning to do with this technology. So let's start off with what is DART? So I don't know if you've heard about DART, but DART is the Double Asteroid Redirection Test. It is funded out of the NASA Planetary Defense Coordination Office. And the purpose of it is to pretty much just demonstrate the efficiency and of the kinetic impactor technology. So what does this mean? It means that in the case that we're ever in distress and the planet is going to burn because an asteroid is coming to hit us, we want to have the technology that we need in order to stop that from happening. And one of those technologies is a kinetic impactor, which is kind of, I guess not really to a scientific community, but kind of fancy way of saying we're just going to build a spacecraft to then destroy it against this asteroid and try to change its orbit. So the spacecraft, DART, will be hitting Didymos B, which is part of this binary system of Didymos A and Didymos B. And the hope is that by hitting it, we can change the orbit of that smaller asteroid around this larger Didymos A asteroid. And we can make observations from Earth to more accurately understand exactly what the effects of this kinetic impact are and understand the technology in the case that we ever do need it. So excitingly, there was recently some commotion in the European Space Agency, actually, that now they're funding a Hera mission, which is going to be a follow-up to DART pretty much. So we are planned to impact in 2022, and then in 2026, the Hera mission is going to go to the asteroid and check out what mess we made, right, after we impacted the asteroid. So what exactly does the spacecraft look like? I just wanted to give you a little perspective because it's really cool to me that we're going to be hitting a 170-meter asteroid with a spacecraft that is a little bit larger than a school bus, but a little bit smaller than the Arc to Triumph, and that is with our solar arrays rolled out. Honestly, if you stand in front of it, it fits in this room just fine. So it's kind of incredible, you know, what we're going to be doing here. And the reason why we're hoping this kinetic impact technology works is because we're going to be hitting it really hard, about 6 kilometers per second, which roughly translates to about 13,400 miles per hour. So try getting in a car going that fast, right? So we're going to be hitting the Didymos B, like I said before, and then we have Didymos A up there for reference as well. So in DART, just like in any other I guess, software project, there's usually a project plan with multiple project phases, right? And as we go through these project phases, the problem is that with time, errors that we find later become more expensive, not only in time, but also in money. I guess time is money, so both, to fix. And so what the Dart team wanted to do was, well, we want to make sure that the flight software developers themselves, before we even get into integration testing or anything like that, we want to make sure that the flight software developers themselves have all the tools that they need in order to quickly develop, test, and then once we get to the actual integration testing with the real hardware, we can have a better understanding of, well, this was working on this environment, so now we just need to figure out exactly where things are going wrong when we're trying to interact with the real hardware. So we want to make sure that we're testing in the code and testing phases of our project, right? To make sure that we catch the errors early and we don't spend as much money. Dart also has a unique nature in that it is a shorter mission in terms of time frame. So you need to make sure that you're being agile when you're developing. And this word agile has been spreading like wildfire all over software, including flight software. So this project definitely had a need for such a culture, because it was a fast-paced mission, and we wanted to make sure, you know, we didn't make any mistakes. So in order to provide this development infrastructure for flight softwares to develop their code and test it often, we needed to create, you need different types of development environments, right? And someone had previously mentioned that these different development environments come with different levels of fidelity. And so I just wanted to briefly say that what I mean by fidelity is just how close we are to duplicating the actual real-time conditions of the mission, right? So we're talking about things like endianness, we're talking about things like clock rate, available RAM, and some of the other things that I believe Ashley just spoke about when talking about their Swirl environment. So we want to make sure that whatever it is we're testing, we have a good understanding of the fidelity level and the confidence in our tests that we can have when we're developing flight software. So in the Dart mission and at APL, and I'm pretty sure a lot of other organizations that work in the space industry, you typically have multiple development environments, right? And we have our Spacecraft integration tests, in which we do actual tests with the actual hardware mounted on the spacecraft, and those tests are great. But newsflash, if you're doing your first test of line 272 in your some C file during your spacecraft integration test, you're going to have a lot of trouble. So there has to be something else, and that something else is typically Swirl, which is the test bed or hardware in the loop, right? And Ashley, like I said, just talked about Swirl, but what we noticed, at least in Dart, was that there had to be something else that we could provide to the flight software developers so that they could quickly check their code. And so we came up with what's called software in the loop, which we actually had a presentation about in last year's flight software workshop, but I'll briefly go over that in just a few minutes. But then that still wasn't enough, because there's some sort of gap in between the two in terms of fidelity, in terms of testing fidelity. So we wanted to bridge that gap, and that's pretty much what we're going to be talking about today. We're going to be talking about PIL, which is processor in the loop. So let's now dig a little bit into each one of these things and how they differ from each other. So just to quickly go over what exactly our hardware in the loop is you have avionics and real-time simulator. So I honestly feel like a rock star with this thing and the microphone. But so what we're talking about in terms of hardware in the loop is avionics and real-time simulator, where we have testbed software emulations for each one of the hardware that we're going to be interfacing with in the spacecraft, right? And as the project goes on, hardware gets delivered, like everybody has been saying, hardware gets delivered, then we can switch out those emulations with the real hardware, and the fidelity of that system then increases, right? Because we're actually testing on the real hardware. However, this starts to happen only when hardware starts getting delivered. So you don't want to be, as a flight software developer, stumped by the fact that the hardware has not been delivered. So that's why we have those testbed software emulations, right? But the problem with the testbed software, the testbeds themselves, is that they're typically very expensive. All the developers want one because we want to make sure that we're testing our code as often as possible, and so there has to be a schedule maintained and all these things, which make configuration and maintenance kind of difficult. And finally, the initial state of the testbed is usually unknown, because if I test my code today and at 3 p.m. somebody else has it, you have no idea what configuration I left it in. So all these things together make up hardware scarcity, right? Now there's a limited amount of test beds that we have, and we still need to get a lot of code done. So what the Dart team created was the software in the loop, which is pretty much what we like to call a spacecraft on a laptop. You need nothing else except from Docker and then all your source code. And so what this is, some of the enablers that allowed us to do this were the Core Flight Executive, as developed by NASA, the Cosmos by Ball Aerospace, and finally Docker. And I didn't put by Docker because it's the same name, but Docker by Docker, I guess. So let me talk a little bit just about what these two last things are, and then we can dig into the real meat of the presentation. So Cosmos is our micro mission operations center. It's what we like to call it. So it allows us to have commanding and telemetry of the spacecraft on our laptop. It is an open source project. It's pretty great. And it allows us also to test everything and automate all of our tests within this Swirl spacecraft on a laptop environment. So that's pretty much what we're using as our micro mission operations center. Then Docker, just out of curiosity, have any of you heard of Docker before? Yeah, oh, awesome, okay. So I'm still gonna say what it is. Docker is a containerization tool. So it is easier with it to create, deploy, and run your application, right? And so the way that I'm going to be using these terms throughout the presentation, so I just kind of wanted to clarify. The way that you can think of a container is kind of like an application or service package that has everything that you need in it. It is kind of like a VM in that you have complete isolation of your environment within this container. However, with Docker and with containers, what you're actually, the abstraction layer is on the OS and not on the hardware like it typically is with a VM. So this makes them a lot lighter and makes them easier to just instantiate and tear down. So we use those in our Swirl infrastructure and also in our processor in the loop infrastructure, as you'll see. Then we have images, which pretty much define our containers. So it has configuration pretty much of the environment that the container is going to be running in, and then a Docker file which defines that image. Finally, there's something I didn't include up there, but there's Docker Compose, which allows you to create a network of these containers and have them communicate with each other, which is what allows us to do our spacecraft on a laptop, right? This network of different containers where we'll be discussing what each container would look like. The final thing we noticed is there's going to be a lot of different things that need to be very well configured. So we needed some sort of standard, I guess, directory infrastructure. And so we came up with this, where the developer just needs to install Docker, clone this flight software Docker repository, and then this flight software, the Docker repository has everything that you need in order to instantiate the spacecraft. It includes the Docker Compose files, which define that network of containers, the Docker files, which we just discussed, utilities, and a shared environment. This is the star of the show, shared environments, because the shared environments is pretty much where we have all of our submodules, and I'm sure we're all, or hopefully we're all familiar with Git and versioning with Git. So submodules, we can plug in all of our submodules into this main repository, and like that we are pretty much, it allows us to plug and chug different source code. So for flight software, for the testbed software, for Cosmos, which is our ground system, we have up there a workbook translator, which allows us to, from XLS, create databases that we can use in Cosmos, and we can actually translate those same XLS workbooks then into like something that we can use in L3. So the purpose behind this was so that in the future, as other missions try to use this environment, they can just keep everything else except for whatever is Dart flight software, unplug that, and plug whatever they have in, right? So tried to make it as modular as possible. So I wanted to take a look, just a little closer look at Dart flight software specifically. So obviously this would live under flight software Docker, shared environment, Dart flight software. And then if we take a look inside that, what we have is two different paths, or compilation build paths, right? And so we have one that's for Spark UT700 RTEMS and another one for PC Linux. And so what this allows us is from the same code that we have in that whatever Dart flight software submodule is, we can create 2 images. One image that we can deploy onto our test beds to whirl, and then another image that we can deploy to run our spacecraft on a laptop. So once you've done that and you have compiled images, then you just instantiate your spacecraft. And so the actual container network looks something like this, where you have your flight software container interacting with your testbed software container back and forth, and then your testbed software container interacting with Cosmos. And Cosmos provides a display to the user so that they can run their tests, they can command the spacecraft, and look at telemetry coming back. So the reason why I have these kind of like on cylinders is because each one of these, the actual code is volumed into the containers, such that, I don't know, I mean, most of you are familiar with Docker, so you know that you can copy code into these Docker containers, right? But the problem with that is that once you've copied it in, that means that that Docker container is going to have that set of code. So what we wanted to do was make sure that when we instantiate the container, we can look at the code immediately just through, it's whatever's in your machine, right? And so what volume encode is, by the way, if you're not familiar with it, is that you can actually access the directory from your host machine from that container. So that's pretty much what we're doing. So what this gives us is something that's cheap. All developers can have one because it's just on a laptop. It literally runs on just your laptop. Its configuration and maintenance is simple, mainly because you don't have to worry about it much. And the initial state is known because you always know that once you've teared down that stack and you bring up a new one, it's going to be brand new. So this makes for faster, reliable development, right? But what's the problem here? The problem is that we're not running on any actual hardware, so then we have lower fidelity. And what we're trying to do is keep at least some level of confidence in our testing. Of course, Swirl does provide some level of confidence in that just normal things that you would test on your flight software development, very rudimentary things. But if you want to test on a more highly fidelic model, you need something that's in between a test bed and flight software, right? So what we decided to do was, okay, well, we created this beautiful modular infrastructure. So what can we do? Well, we want to keep Cosmos for the user to interact with the spacecraft, but let's replace the flight software container and let's plug in some real hardware and plug that hardware into our computer, and then now we have this processor in the loop infrastructure which allows us to just run on real hardware, or at least hardware that gives us a higher level of confidence whenever we run our tests. And so the question now becomes, well, I mean, what hardware could we possibly use for this, right? And it just so happens that as we were working on this, there was another team of very bright engineers at APL that were working on, well, let's try to find something that's a little more inexpensive to get something similar to where we actually run our flight software, right? And so what they came up with was Smart Fusion system on a module. And so it's practically just an embedded software Leon 3 processor programmed into an FPGA. And it's a variant of the more expensive Leon 3 boards that we use to run our flight software on the test bed. So, 5 minutes? Okay. So this allows us to connect via Ethernet and USB. I might have to speed up a little bit. So what this allows us to do is it gives us a more loyal environment, right? Something with more close clock rate, endianness, and real times, which we don't get from Swirl. What that hardware team also did was they created this custom bootloader and NetBoot image that allows us to load and run the image without Gurmon, and it allows us to update the image without having to worry about Gurmon either, because all we have to do is pretty much just we drop it into a directory, and the processor immediately knows something changed there, so it'll reset itself. And then all configuration setup is what they didn't realize that they were doing is they were making it very, very easy for us to configure and set everything up using Docker, because if it's just as easy as moving files around, Docker can do that, right, on runtime. So we decided, okay, let's mix these two things, and then we have pill. So what that looks like as a change in your file infrastructure is now you just have, in that same Dart Flight software directory, you now have a path for the Smart Fusion image. So now you can build 3 kinds of images that you can deploy, where the Spark Smart Fusion RTEMS image is very much like the UT700 one. And so what does this get you? It means that you can get from something like this to something like that, just running on your desk, right? And you have you keep that level of fidelity. So something else that we're achieving is we're bridging that gap. So now we don't have that gap in fidelity, right? You can choose Swirl, you can choose Pill, you can choose Will as you go, as the project matures, and as you go through the phases of the project, which is what you want to do. You don't want to slow down because you're waiting on something else. You want to continue to develop. Now the question becomes, well, then why use Swirl, right? I mean, I could just use Pill, so why use Swirl? Like, what's the purpose of doing that? So, well, the purpose is with Pill, you get a higher fidelity model, but if you want to instantiate something quickly, and if you want to have a bunch of them in your machine, you can use Swirl, because with Pill, you're limited by the single FPGA. But of course, usually when you're developing anyways, you want to just test on a single, you're testing on a single spacecraft. It's not like you want 50 of them on your machine, although you can run 50. I mean, maybe you want to hit the asteroid 50 times, but so there's still some win on both sides, right? And the point is that you have that array, you have that choice to make as you develop. So what this allows us to do as well is that we can integrate all this into our continuous integration pipeline. So in Dart, we use Bamboo, which is pretty much just a continuous integration orchestrator, I guess you could call it. And it allows us to run a bunch of flight software tests, unit tests and app tests. These unit tests are on the code, obviously, and then the app tests would run using the Cosmos test runners, which allow us to send commands and expect some telemetry back and do application tests like that. And now we're not only doing it on Swirl, we can also do it on Pill, on the real hardware. And how we do that is we have different, wherever the Bamboo agent is running, we plug in a Pill, and then we run on our Pill environment. So in the future, what we would want to do is grab a bunch of those and create a Bamboo army where we just have Bamboo agents everywhere with a Pill plugged into them, and we're just running tests every single time that some sort of software change is made. And we already do this with Swirl, but we would be increasing our fidelity with Pill. So we want to make sure we work around some of using Docker tools, which if you're interested in, I can talk to you about if you approach me, because I'm running out of time. I have 1 minute. Okay, so and we hope that other missions start adopting the technology as well. Finally, I'd just like to thank the NASA Planetary Defense Coordination Office for funding us and saving us, hopefully, in the future. APL, the DART team, and the Flight Software Workshop for inviting me here. Honestly, it's a pleasure. I love the wire because I feel like a rock star, and I'm talking about something that I'm passionate about. So if you guys have any questions, let me know, and if you want to approach me at any point, feel free to do so. Yes, it will transfer kinetic energy to the dynamos. You said between an FPGA. I don't think the mic is on. So between the FPGA and what? Honestly, the reason why we decided to go with this is because there were efforts at APL that we had already undergone, and so we wanted to adapt that technology. And also the NetBoot Loader image made it really easy to integrate with Docker. So that's pretty much why we decided to go that route.
Other questions?
I just want to say, I have a presentation that's after the next one, and it's about a QEMU-based processor in a loop test bed. Woo!
Cool.
Get the best of both worlds.
Other questions? Nope. Great. Thank you.